My name is Almgren. I work at Lawrence Berkeley Lab. I'm also the Deputy Director of the AMReX Co-Design Center, which is one of 6 ECP co-design centers. ECP is the Exascale Computing Project. A couple things. So first thing I want to do is I'm a big fan of word searches, so I'm going to make a plug for the word search over lunch. Are we allowed to tell them? There are 32 possible answers. We decided not to give you the words, so you have to figure out what words are in there. They are all relevant to today. They are either package names or project names or words that apply to good software. Comment 2 is the way we're going to do this hour is I'm going to give about a 15-minute introduction to AMR and specifically AMReX. And then Don Willcox and I are going to sort of tag team. We want to walk you through 3 hands-on exercises. Each will be roughly 15 minutes. I'll give a little introduction to it. Don has done all the heavy lifting for him, so all technical questions will go to Don. And then we'll finish up right at noon, and then we'll have Dan Reynolds after that. Since I'm not going to leave time for questions at the end, I will expect you to interrupt with questions. Do a hands up. If I don't see you, wave. So we'll take questions in the middle, either during this intro part or during the hands-on. Okay, so AMR. Some of you know this, adaptive mesh refinement. What I have found is that there are a lot of misconceptions about what AMR is. So I'm going to try and tell you what it is. And you'll notice there's a certain slant in my presentation because I would like to dispel some myths about what AMR is. More generally, we're going to talk about block-structured meshes. So everything I'm saying, which applies to the software package AMReX and also applies to just sort of these structured meshes in general, doesn't have to be, the meshes do not have to be adaptive. More broadly, I'm talking about block decomposed meshes. The key is that they're structured. And so the software things are very useful for AMR, but they're also very useful if you're doing single-level domain decomposition. So setting the stage, Mark gave you a great 1D example to walk through. And as we'll talk about later, if you want to write a 1D code, you're probably going to do it the way Mark did. You're going to sit down and write it in 10 minutes. You're not going to go search the web for some 1D software package. The problem is that for most of us who are on this side of the podium, and for most of you either now or in future, the problems that you're going to solve are hard. We're not solving the 1D heat equation. We're typically solving in 3 dimensions. If we're doing a physical system, we're solving in 3 dimensions. Characteristics of these problems, they often couple multiple physical processes, multiple spatial scales, multiple length scale. You hear about multi-scale, multi-physics, multimodal, multi-this, multi-that. So we're trying to put together these complicated pieces. So back in the day, you could do single physics problems. You could do flow in a box. That was great. You also had architectures that were much easier to program for. So you wrote it back, so yes, dating myself and probably you, there was a world before parallel. There was a world where we got real excited because the way to make things fast was to vectorize. As long as you wrote all your loops, you took out the if tests, and they vectorized, that was it. And I still remember when we were developing software, we said, what if we should make a parallel version? Parallel, that's a fad, that'll go away. So you guys are growing up in the world of parallel. It's only going to get more heterogeneous and more complicated. So the challenge for you guys is you want to solve, I hope you want to solve the hard problems because the hard problems are the interesting problems. You can't do it all. That's kind of the message here. You want to build algorithms. You're going to embody those algorithms in software, whether you're the only one who uses it or you share them. But you want to solve hard problems. It's really hard to start from scratch. If you do that at the beginning of your PhD, maybe by the end of your PhD you will finish it, maybe by the end of your postdoc. But then you sort of haven't gotten as far as you could go. Okay, so let's say you want to solve a problem and you don't want to start from scratch. Well, you do want to start from scratch. Usually the first thing you have to do if you're solving a physical system is you have to decide what is your physical discretization. So not all simulations use a mesh. There's a whole category of things that are pure particle simulations or have discrete elements that are not connected in a mesh. So we'll put that one aside. You'll notice I've gratuitously pulled images off the web. I've tried to give them credit everywhere, so make sure you notice that. If you decide you want a mesh, you want to discretize space into something where you have little elements, typically the next choice is structured versus unstructured. There are trade-offs, and I'm not here to tell you that one is better than the other. In fact, 2 years ago, we had the structured mesh session and the unstructured, and it was crazy. So they've gone to this system of alternating year by year. So this year, you get the structured mesh pitch. As Mark pointed out, the 2018 at-PESC lectures will have the unstructured mesh. But the idea is that you should understand the trade-offs. So why would you choose a structured mesh? First of all, it's a lot easier to write discretizations. If you want to do an x derivative, you know that I plus 1 is to the x side, the high x side of point I. So you say, it's phi at I plus 1 minus phi of I. You've written an x derivative. Life is simple. You have simple data access patterns. For those of you who are computer scientists, yes, this is obvious. For those of you who think more about the math side, you now have to care, I guess is the message. So you have to care, what Jim was talking about, how you pull the data in and out of memory matters. So if you want to write a fast code, you're going to have to care about how you're accessing the data. In the world of increasingly heterogeneous memory layouts, you're going to have to care even more. I'm going to talk a minute about why this uniform discretization is even a thing. And then the other thing is, a lot of people say, well, I use unstructured mesh because I have boundaries. It depends what type of boundaries you have. So unstructured mesh is really designed for complex domains. It handles geometry much more natively in a sense. The fact that you have geometric information, that you may have bounding walls or you may have objects in the flow, that does not preclude you from doing structured mesh. It means you're going to use a different algorithm. Depending on what you care about, that may or may not be good enough. Okay, so advantages for unstructured, you can fit this mesh to any geometry. You don't have to be cutting square cells. It fits. You don't have special issues at domain boundaries. Now, in some sense, the trade-off is, well, every cell is sort of a different shape or different size, so you have work everywhere. But the cell boundaries align with your geometry boundaries. The problem, of course, is you have more bookkeeping because I plus 1 minus I does not necessarily give you an x derivative. You don't even know who your neighbors are necessarily. So you have bookkeeping to maintain that. And in some cases, the geometry generation is time-consuming. There's a lot of work going on in that field to bring that time down, especially for time-dependent geometry. Okay, this is part of the dispelling the myths. When people think structured mesh, everyone first goes to the top left. That is a structured mesh. And if you Google structured mesh, that is the first thing you will see. The point here, so we call that logically structured. Well, sorry, that one's structured in every possible way. When we talk about structured mesh operations, what we're thinking of is logically structured. So I have a sense of I plus 1j, I minus 1j, but that doesn't mean it has to be physically rectangular. So there are 3 examples here. This left one is something we call stretched grid. It's where I keep the same number of mesh cells. I don't have to have a uniform dx. Now here, the dx is independent of dy. Actually, it's not. Pause on that. So anyway, but I still have this relationship of phi at I plus 1 to phi at I. Same thing in the middle. Again, I can have metric coefficients. When I'm writing down my algorithm, I have to include those metric coefficients, but I know that I plus 1 is next to I. And again, third thing on the right, we can have cylindrical coordinates, we can have spherical coordinates. Those are still categories of structured mesh. Okay, another thing, you do not just have to have a rectangular geometry. This is something that we call grid pruning. This is still a structured mesh. What I've done in this particular this is a very simple schematic of a chemical looping reactor. You'll see there's a lot of empty space in the middle. I don't need to do any work there. I don't want to allocate any data there. This still fits within my adaptive mesh paradigm. So the point is, structured does some good things for you. It doesn't preclude as many things as you might think. Okay, why this obsession with structured mesh? What do we like? Okay, one of the things that happens, and if those of you who take a numerical analysis course, you remember that Mark gave us a centered derivative in space. Okay, it's kind of a standard derivative. And if you look at numerical analysis 101, you can write out why is this an approximation to a second derivative. So you write a Taylor series for phi at I plus 1, a Taylor series for phi at I minus 1, you difference those, and you see this term, this phi xx term that has a, I'm sorry. Sorry, this is not a second derivative. This is a centered first derivative. I apologize. But you see a term that has the difference in the mesh spacing. So this is just a first derivative. It's a centered derivative, but not a second order derivative. There is a term that sees the difference in the mesh spacing. When the mesh spacing is uniform, that term cancels out. That term is 0. So what we generally say is that when you have delta x relatively uniform, you get sort of an extra order of accuracy. Now, if that difference is very small, that term can be very small. This does not preclude doing things with mapped grids and such, but it's a reason why we sort of like having uniform grid spacing. So now you start saying, well, I'd like uniform grid spacing, but I also have seen a number of examples where I want finer mesh spacing in one place than the other. And that's in some sense where block-structured AMR comes from. So the idea is I like having delta X constant. I like this uniform property. A, it's really easy to discretize. B, it's higher order. It's going to get rid of that one term, gets me one order of accuracy. Distorting the mesh in some cases is the right answer. And again, there are cases where unstructured mesh is the answer. There are cases where distorted mesh is the answer. But if you can avoid it, that's nice. So block-structured adaptive mesh refinement says we're going to use block-structured means in every block, every rectangular region, dx is uniform. So I have these local structured, locally regular patches, but I'm going to refine the mesh in regions of interest. So where I care about, I'm going to put finer grids. This local regularity is great for passing data to GPUs, for example. It's locally structured. You've got really good access patterns. It's got easy discretization. It naturally allows this hierarchical parallelism. For example, MPI plus OpenMP, you say I'll distribute grids to MPI processes, and then within the grid, maybe I'll use OpenMP on tiles. Maybe I'll send that whole block to a GPU. If you think about now where you have to do the extra work, with a grid where delta X and delta Y are changing, you have connectivity, at every cell you have to ask, who are my neighbors? What's the distance to the neighbor? How do I discretize that? Here, you're doing that only at coarse-fine interfaces. Now, that can be a downside. You have to do extra work at coarse-fine interfaces, but you've localized it. You know exactly where you're doing it. And again, the bookkeeping is not bad. You're not keeping track by cell. You're keeping track by block. And I use the word block, grid, patch, and box interchangeably. Those are all the same thing to me. So you have to keep track of where are your grids, but that's a relatively small amount of metadata. Just because people may have seen pictures of AMR before, they're sort of, in the world of block-structured AMR, there are two flavors. On the left is AMRex's version. On the right is Flash's version. If you know, Flash is a code actually out of Argonne, University of Chicago. And we've actually talked about trying, they're both block-structured AMR. We've tried to come up with different words. The fundamental things is, in the Flash version, the grid sizes are uniform, and there's a unique, every child has a unique parent, i.e. only one. In the AMReX form, you can have these overlapping grids where one child grid, which is the finer grid, might have two or more parents, and the grid sizes can be different. In terms of the bookkeeping across levels, again, on the Flash side, this the quad tree or octree. You have this unique relationship. It allows you to find your neighbors by traversing this tree. In the patch-based form, you still have to know who your neighbors are because you need to know when you're going to fill boundary cells and things like that, where you're going to get them from. You can cache that information. It turns out you can do it very effectively. It turns out I gave a talk at Cyan Parallel Processing a couple years ago, and it was held in Paris. And somebody came up to me near the end of the meeting and said, the Europeans are really mad at you. I said, because I'd given the plenary about AMR, and I'd called it AMR. I said, what could I have possibly said? They said, well, to them, AMR always meant Octree. And now that you've gone and given this plenary where AMR meant block structured, people are starting to talk about that. And they didn't like that because they, so we took their, according to them, we took their word. But anyway, so these are both legitimate styles. And it turns out, in fact, AMReX as part of as ECP is, Flash is actually having a new AMReX layer under it because everything that you can do with the Octree stuff, you can actually support with something like AMReX. You just bypass some of the more complicated logic. Okay, and then one final thing is, if you start to say, okay, so I have this, but I really, this variable is really smooth, but this one I need refinement. So the phrase AMR for one does not have to mean AMR for all. You can, once you have this ability to play with levels and data structures and all of this, you can say, I want this variable to be refined, but I don't need this variable to be refined. So there's all kinds of games that you can play with it. And as you'll see on the hands-on lesson, this is not your grandmother's AMR. This is the new modern version. So in this case, what we're doing is we want to resolve the geometry. We're doing that with the level set. So we do that with the fine grid. But the flow and the way we organize the particles, we can keep on a coarser mesh. And so we have sort of two different uses of resolution there. Okay, time stepping. You have a whole hour on that afterwards. The comment I want to make here is when you use an AMR package or you write your own, the fact that you're using AMR doesn't tell you what your spatial discretization is, whether you're using second order or fourth order derivatives. It doesn't tell you what your temporal integration is. And again, a lot of people think that, oh, AMR means, forward Euler or this or that. Back in the day, when AMR was first invented, it was used for hyperbolic conservation laws. And those were always advanced with an explicit conservative update. So people had in their head, AMR only works for explicit. We're past that now, okay? So the fact that you're using AMR, in fact you're using block-structured grids, doesn't tell you how to discretize your system. And there's going to be a whole talk about that. And that, in fact, one of the fun things is that sundials, who are experts in time integration, we can couple those with AMReX so that sundials can use this higher order time stepping to drive AMR integration. There's ways to put this all together. In the space of AMR, though, there's usually one question that you have to ask. So if you're designing an algorithm and you say, I really want high resolution in this one region, the main question you have to answer is your time step going to be uniform across the whole domain, across all levels, or is it going to be, we're going to do what we call subcycling, which means that as delta x gets finer, delta t gets finer. There are trade-offs. If you do not subcycle, if you use the same DT, every operation can be a multi-level operation. So that can be really handy. If you do subcycle, you have certain advantages in terms of advection schemes. They tend to operate better at higher CFLs. There's ways that you can write the algorithm that seem more natural. There's a trade-off. It's just sort of like with Refinement. When you get to the end of a time step, you have to synchronize between coarse and fine levels. That has some additional operations. But that's sort of a choice that you make when you're designing your algorithm. OK, again, AMReX itself has a history of a number of applications. We've got low Mach number combustion. We've got basically cloud formation, moist atmospheric physics. And then down here, we have something that is microstructure evolution in solids. Very different applications. There are a lot of things that you can do with this. You can also add particles. The other thing you can do at the bottom I mentioned, I'm talking fast because we're running out of time, is you actually don't have to do the same physics at every level. So you might have a fluid representation and a particle representation. I mean, if you can conceive it algorithmically, then you can program it. OK, software support. So maybe I've convinced you that you don't want to write all this from scratch. So if you say, I like this idea, but I will guarantee you don't actually want to write this from scratch. There are a lot of packages out there. I didn't go through and list them. What they all do, they all give you data containers, they all give you data iterators, and they all manage some form of regridding. How do you destroy grids, create grids without losing the data that you had? They differ on a number of things. Do they only support self-centered data? Do they have faces nodes? What types of time steps? There are some packages that are wired to only support non-subcycling. Now I'm talking about software packages. Do they have to have the same grids for all the variables? What degree of parallelism? Are they on GPUs? Are they have OpenMP? Task iteration support, we won't have time to go into that. What are the load balancing criteria? And what other features come with it? So AMReX has, to my mind, almost everything you would need. I'm going to leave the slides with you so you can go through them. Mesh data, cell centers, faces, nodes. Particle data, you can have different types of particles. Geometric data. The comment here is the upper two are unstructured meshes. You see when we change the object/obstacles, you change the mesh. The takeaway here is if you change the obstacles in a structured grid, the mesh itself doesn't change. You create different intersections, but the mesh itself is fixed. Just a different AMReX, you operate on data through iterators, which means that at the application level, you don't see whether you're operating on the CPU or the GPU or whether you're threading. That's kind of hidden in the iterators. The bookkeeping is handled there. Regridding is handled. OK. Also has a dual grid approach. We use this for particle load balancing. Particles can live on a different distribution. OpenMP, CUDA, GPUs, things like that. Also has linear solvers, which we're going to use in one of the examples. And the I/O format, we have a native format that we write out. It's supported by the tools that you learned about yesterday, Visit and ParaView, and also YT. You're going to see all of this in the examples that Don's going to show you. I'm going to skip over this. One of the comments is, so you're going to see me again at in the panel and then also again in the wrap-up. So if there's anything that you want follow-up on, let's come back to it then. One of the things we've done is we're moving from Fortran to C++, something we can talk about later. This is a statement about how you think about OpenMP versus GPU parallelism. Again, we can talk about that later. This is what a loop looks like that's the same on CPU and GPU. And the hands-on example, we're going to have 3. And I'm just going to sum these up, and then Don's going to take over. So the first one is what we'll call traditional AMR. So it's scalar advection. We're going to have multiple levels, multi-level fluid mesh data. We're going to have subcycling in time and dynamic AMR. And then the next two are kind of for fun because I again, want to make the point that AMR is not just, this first example is kind of what we think of. So off to the races, we're going to put some obstacles in the flow. We're going to use the linear solver to solve for a flow field, and we're going to race some particles around them. And what you get to do for hands-on is you can determine the placement of the cylinders. And so the game is, and I don't know if we figured out the point total, but if anybody can figure out what configuration of cylinders gets the first particle to the finish line fastest. Something to think about. And then the third example is AMR Pachinko. Anybody know what Pachinko is? I could picture it, I couldn't remember the name. Okay, you're gonna see what, so we made an AMReX version of Pachinko. Balls are gonna fall from the top. And this is an example where you have particles, but you don't actually have a fluid. But you can still use all of the constructs that we have because you're still decomposing the domain into these spaces. Okay, takeaway while Don comes on up. So different problems have different needs. You structured mesh unstructured particles, you do what works. Structured mesh is not just flow in a box anymore. There are a lot of AMR packages. Of course, I'm biased. I think AMReX is the best, but there are a lot out there. You can Google them. You can find them. And interoperability, you'll see that as a theme. So we're going to have sundials talking to AMReX. We're going to have Petsy Tau talking to AMReX. That is essential, and we'll come back to that in the takeaway. And now we're going to go back to Don. So I'm going to narrate for a minute as soon as we bring up. So the first example, again, there's scalar advection. We're going to prescribe the velocity field. And we're going to put a scalar drop in there and see what happens and see how the meshes respond to this. It's a 2D example, so you can imagine maybe a 3D fluid flow, but it's thin enough that we can view it as a 2D problem. Okay. So what we're going to do is you all have the, if you went to the website that is called the Math Packages Training, you should all be able to see this. Then Don's going to put up his Cooley window on the right-hand side. The executable is made for you. So Don, you ready to show them where to go?
Yes.
Okay.
So the first thing that we're going to do is, this is my home directory, is we're going to bring in everything from projects, @PES 2019. Let me make this text a little bit larger. Projects, @PES 2019, math packages, training, hands-on lessons. So we're going to refresh everything from there. I'm up to date. So do that first. And then let's go into hands-on lessons. And we're in the AMReX subdirectory there.
Okay, first question, anybody not following this? Anybody who is following along not there? Okay, Kyle, just need a minute?
Is this a different, if we already, oh, it's the same one.
Yeah, they may have hands-on lessons already, yeah.
Right. If you already have it, though, I do recommend that you rsync it from the projects directory.
You periodically change things there, so
right.
If you're asked to rsync it again.
Right. So, off we go. So I'm already in an interactive session with 4 MPI ranks. The first thing we're going to look at is multi-level scalar advection. And so this uses mesh data and dynamic AMR with subcycling. This problem is a drop of dye that is being advected in this velocity field. It's a divergence-free field, and so we advect a blob of dye, and that's what you're going to see. So we're going into the AMR advection subdirectory here. There's a main executable, so we can do MPI exec and 1 and give it the inputs file. And we'll see lots of output that gets printed as time stepping goes on, and at the end we print out the total time. We've gone 120 course time steps, and what you see here is time stepping information printed for every level in this. So this is the picture that we're doing. This is what we're doing. We have a blob that is being advected clockwise and then counterclockwise in a velocity field. And it's on multiple levels in the AMR domain, and you can control how those levels are refined. So that's an interesting thing to play with here. Here are a set of parameters that are useful for you to play with. For this example, you can play with the number of cells in the domain. This is a 2D problem, so 128, 128 would be an interesting set of inputs. You can change the max grid size, and so on. here, phi error, you're telling this example what values of the field to refine on. So with these values of the field, you get refinement at those contours of this blob. So we've just run this. Now let's make that movie. So we're going to do make movie. And this will run a visit script that builds a movie for you. And it should take 30 or 45 seconds. And then you'll get an MP4 file in this directory that you can SCP down to your laptop and run. So is everyone following along so far? Are you able to run it?
The make movie command isn't working.
OK.
Yeah, make movie isn't working.
They've not executed it to determine proper environment settings.
OK. You may need to add visit to your soft environment. These are the contents of my soft.coolie file.
So is there anybody who still needs visit help? OK.
If you'd like to run visit in client server mode from your laptop to Coolie, there are instructions down here for how to do that and what commands to execute.
Has anybody been able to make the movie? A couple people. OK.
Wow. Has anybody tried other sets of inputs to see how the movie changes if you change the gridding or change the maximum number of levels? So this movie finished for me, and I get this file, AMR_advection.mp4, in this directory. And to save time, I'm not going to copy it down to this computer. But I'm going to show you this movie on my local machine, where I copied it down. So you get a blob. Let me run it and pause it. You get a blob, but the gridding here isn't particularly interesting. Remember, we only ran it with one MPI rank. So you can make this much more dynamic and actually see how the gridding evolves in time if you change the refinement criteria in the inputs file. So that's the next thing that you can do in this example. First, let's take a look at the inputs file. And there's some stuff in here under refinement that you can control, like AMR max level. The level numbers start at 0, so a max level of 2 means 3 levels. Yes?
So what does the physics seem to reverse itself after that?
Yes, that's coded in. It's supposed to reverse itself and go back to its starting position. I'm sorry?
Sorry, is it physically we're simulating it forwards and backwards, or is that
Yes.
No, to clarify, we have a time-dependent flow field. So we hardwired that velocity field in. We like it because then you can compare. So if you're debugging a code, you ask, where did my blob come back to? And if you've got a bug in your advection scheme, you'll find out the blob doesn't return to where it started. So we hardwired in the velocity field that was specified initially. It has a cosine of pi t in it. Yeah.
So if you'd like to be adventurous, what I recommend you do is go down here to Things to Explore and try this out. So this time, we want to actually give the problem enough work that we can run 4 processors on it. So we're going to change AMR.nCell to 256, 256. So this is a 256 squared grid on the coarse level. And then we're going to set the max level to 3. So we have 4 levels of refinement. And we're only going to go out to a max step of 50 steps so that we can keep this reasonable. This will take like 10 seconds or so to run, or less for 4 MPI ranks 2 and 1. And so try that with a different number of MPI ranks and see how the time to solution at the end changes. Is anybody still with me?
So we might want to leave some of this for tonight, and then we can move on.
Okay. So, all right. How many people have made a movie so far? Oh, wonderful. Okay. All right.
How did you not have your default thing be jet? I'm like in jet color map, and it's the worst. Like, how do you have yours like you?
Oh, I'm not sure.
Visit color map, Mark?
So it's probably, you probably have your default set to not have that. And so you could set the color map in the Python script as well. So it would be under the pseudo-color attributes. I can show you how to do it. Yeah. Want me to come over and show you how to do it?
Well, actually, so we're going to move on to another example right now that doesn't use visit. But in our 2 hours or 2 hours tonight, so all the code will be there. This is a fun thing to play with, so you can change number of processes, total size of domain, size of your patches, how many levels you have. It's a fun way to experiment with how AMR treats these things. So in our second example, we're doing something a little bit different. So now instead of having, we're actually going to do a single level example. We're going to have a flow field that is computed as potential flow around obstacles, and we're going to advance particles through it. And one of the things you'll notice, for example, is the particle advection scheme, if you dig in the code, is very, very simple. There's an opportunity there to maybe do a higher order particle scheme. But here what we're going to do is, let's scroll down to the movie for this one. So let's say you have a channel and you want particles, you want the flow to get from the left side to the right side as fast as possible. And I'm going to specify that the inflow on the left is 1. It is 1 horizontally. And all I'm going to give you is 9 cylinders that you can place. They're just obstacles in the flow. Here they're displayed as hollow, but the point is the flow has to go around them. And we're going to use the particles to measure how do you get to the far side first. And you can imagine this could be tracer advection. You have some contaminant that's leaking, and what you care about is when does it first contaminate the far right side. We have numbered the cylinders. If you want to scroll down a little bit. We've numbered the cylinders. They are, I think I did them 0. They are 0 through 8, so 0, 1, 2, 3, 4, 5, 6, 7, 8. And you can specify those at runtime. So if you look at a sample run, Don, you want to go to that directory?
I'm here. Yes.
So why don't you choose some set of obstacles? So we'll go in, and he's going to do an example with whatever obstacles he chooses, and we'll see what the output looks like. And you just need to put a set of integers there. If you put an integer that's below 0 or above 8, it will balk. If you don't put any, I think it will balk. OK, go for it. So what we saw there, the first thing was the multigrid solve. We're solving a Poisson equation to get potential flow. One of the opportunities for tonight is to use an alternate multigrid solver. Here we're using the AMReX native solver. We've got a hyper option in there that you can try later. So you'll see the very last line is we have a winner and the winning time is. So you can imagine going from 0 to 2 with a speed of 1, it would take you 2 seconds. So here we've done something to speed up. It only took 1.75. So we've sped up the flow. We've gotten the first particle there first. If you want to look at a movie of what happened, so just in case you like playing with the viz tools, we've got detailed instructions. Don, if you scroll down for a minute here, we have gory, detailed instructions of how to visualize everything you're going to see. Don ran ParaView, captured the instructions into a Python script because it takes a long time to type all of that. And let's see.
So
Go ahead.
this will take about 30 seconds or so to run. I can show the sample output for what this.
So 1.75 is our current best. Anybody get better than that? And if Mark has enough prizes, we are going to have a prize for the fastest time, but you have to be able to show it to us. He's got enough prizes. OK, so one of the things for tonight is if you want to try running this in different configurations, what is the fastest time you can get? One of the other points that this makes is it's nice to have a simulation code. You can run it from start to end, but you often want to do something with it. So in this case, we want to optimize. We want to find the fastest configuration. And so again, it's that point that Lois made that building the simulation code is part 1, but part 2 may be an entirely different process that just uses the simulation code as a tool. If that's what you're interested in, you don't want to spend your entire PhD, your entire postdoc writing the simulation code. OK, how fast did you get this time? Oh.
Oh,
You get your movie?
it made the movie, yeah.
Okay.
So continue though, I'll need like 10 seconds to copy it.
Okay, anybody have bet faster than 1.75? What do we got, Lucas?
1.44.
4.4? Daniel? You got 4.4? Oh, everyone's getting 1.44?
That's the default.
Wait, what is it?
It's the default input.
That's the fastest? Seriously?
It's the default.
I know, but you're saying the default is the fastest?
Faster. Wait, faster. Fastest.
Is it the fastest so far? So maybe I'll move the cylinders for tonight and just change the problem a little bit.
So this is what we ran with just these 3 cylinders.
And one of the things that you can see here is the mesh is colored by the velocity field. That's the magnitude of the velocity field. So we've got 3 things going on in terms of the viz. We've put the obstacles there. Those are VTP files. We've put mesh data, and then we visualize the particles moving. OK, so we may have to play with that a little bit later. I may have to make that one harder for tonight.
Yeah,
OK.
we can do that. Did everybody get a movie?
So is Paraview working for everybody? Yes? Anybody having problems with Paraview?
The output file name is off. It's this file, off to the races.mp4. Yeah.
Arby doesn't have any particular version.
Yeah, one of the takeaways with this, actually, in the process of putting these together was writing and running the code was really easy. Getting to the point where the viz process was smooth in a mode like this is actually really hard. And I think that a lot of people find that in your workflow, you get your code working, and then trying to visualize it and trying to visualize it so that you can see what you want to see and ask the questions you want to ask, that can be a little time consuming. OK, so let's move on to our one last example. Or do we have any more?
OK,
Oh, have you shown your move? Let's see.
I just showed it. I can show the one with. This is what it is
Okay.
by default. So yeah, this is for reference.
So things that you can play with also, and I think I put these in the notes, is suppose you want to color the grid by the processor. Right? There's an easy way to do it. What we've done is we've saved the processor ID as a scalar field just so that we can easily visualize it. So one of the things you can do is ask, what is the domain decomposition? And what I will give you a preview of, but you'll have to look at yourself. The domain decomposition for this one is going to be relatively straightforward. It's a little bit different in the next example. So it's something that's kind of interesting to look at and say, why did it choose to decompose in that way? And that's something that we'll see more in the next example.
OK.
And the instructions should be there. You'll have to go through visit yourself, or you would have to edit this script to be able to visualize the processor field as PROC as opposed to vel. Is that something they can do in that script?
It's not.
Okay.
You'll have to edit the script or go through these examples go through the manual steps to use Paraview to visualize this.
Right.
But all of that is on the website. So.
OK, so our one final example is AMReX Pachinko. So Pachinko is I believe it was originally a Japanese. So it's a Japanese gambling game. The idea, it's like a vertical pinball machine. So the idea is actually in the real game, you would have something where you'd launch the balls up to the top, and they fall down, they bounce off obstacles as they fall. So in this one, the obstacles are fixed, but you can place the balls. The way that you place the balls is, if you look at you do an LS, oh, you've got an LS there? There's an initial particles 3D file. So I've just given you 10 particles to start with, and these have you'll see there, they have a position. I've put them all at 1.9, which is up near the top. And they're going to fall, and it turns out to make it realistic, you have to make sure that you include gravity, because otherwise they bounce down, they hit, and they bounce back out of the domain. You have to have gravity, and the other thing that was interesting to me is in trying to make this look sort of physical, you have to make sure that the collisions lose energy. So you have to, otherwise they're a little too chaotic and they don't do kind of what we expect. So what we've done is, these are particles released, they have an initial velocity field, they're falling under gravity, and when they hit a cylinder or the wall, they bounce off and they lose some of their velocity. I think I have a 90% multiplier in there. And it's interesting, you can see some of them kind of get caught bouncing between two cylinders. The reason that's a little glitchy is just because of the rate. We're just not writing out every frame. So the solution itself is fine and resolved in that, but that was to make the movie.
Right.
So Don, how do we run this?
MPI exec, to make the picture you saw up there, 4 processors, main 3D.exe, and then inputs 3D. And so this will run and advect these particles. So every 10 time steps, it prints a dot, and then reports how long it took. So you'll notice it said writing EB surface. So this is writing the surface for these cylinders. So that gets read by the movie script. So you can do make movie again. And this is another pair of view script that takes the output from this, which is the particle positions as a function of time as they fall down and bounce around. And so ParaView will make this movie for us. And while it's doing that, we can go and see what this should look like.
So can anybody tell me, so the background here is colored by processor ID. So this was a 4-processor run. Can anybody figure out why that's the decomposition? Anybody recognize that? So there are a lot of different ways of assigning grids to processors. So in our world, one grid is assigned to only one processor. So we don't split a grid. A grid is like a 32-cubed set of points. We don't split that across processors, but we might put multiple grids on a process. So here with only 4 processes, and I think it's something like 40 grids, we have 8 grids, 1, 2, 3, 4, 5, 6, no, 10 grids per process. So we have 40 grids total. There are a lot of different strategies for how you lay these out. And this one, in fact, is the, the Morton Z with Z ordering. And if you look at what Z ordering does, it will typically draw a Z shape, and then it will recursively draw finer and finer Zs. And the idea is you can't a priori say, I want to decompose, like take the left grids, the middle grids, the right grids. I can't automatically decompose in one direction, because in 3 dimensions, you're going to be talking to other grids in 3 directions. And so the idea is you want some distribution that gives the same number of grids per process, and that we've achieved, 10 per, but we also want to respect the communication patterns. And I have to, when I looked at this, I thought we had a bug. I said, there's no way that's the right answer. Of course we should be stacked. It turns out if you don't have 5 grids across, if you have 4, it will do something slightly different. But it's one of those things that when you have a package, there's some kind of domain decomposition happening under the hood. The good news is you don't have to decide it. The bad news is sometimes you won't understand it. Another comment is here, it's actually really silly to decompose. What am I choosing to decompose? I'm decomposing spatially, and I'm giving every grid, in some sense, a cost function that is just the size of the grid. So I said, I'm putting equal work on all the particles. I've got 10 grids per process. In some of the grids, absolutely nothing's happening. There are no particles there. There's no work there. So one of the things when you're assessing a package, for example, is do I have a way of load balancing on something that's not just the size of the grid? Because in this case, what I really should be load balancing on, let's say I'm running with 100 million particles. I really want to load balance on the number of particles. And so that's something we call the cost function. And again, in AMReX, as in many packages, that's something that you as a user can go in and say, you know what, I want to load balance based on number of particles. I want to make sure that I have the same number of particles on every process. We haven't done that here because it's a small example. It's a small example because otherwise to visualize it, we cut into Dan's time. We didn't want to do that. OK, what else can we play with here? Oh. Nope. Nope, there's no randomization. It's just doing what it does. And one of the things you can play with, actually, I was going to do this and I ran out of time, is how evenly distributed can you get them? Because if you look at it, I've deliberately made the cylinders, they're not quite symmetric. And you can see that more particles end up in that right corner. And in fact, two particles, actually, in two locations, you'll see that two particles land on top of each other. If you visit in 3D and you rotate it, you can see that, so the particles do not see each other. That's why they can coexist there. But it was interesting to me that in two different cases, two particles basically ended up in exactly the same spot. So can you sort of reverse engineer this to figure out if you wanted it, here we're starting them uniform on the top, how can I get them more uniform on the bottom? What would I have to do on the top? So it's an interesting thing to think about. And that's something that you can play with. And this one doesn't have a command line interface. You just go in and edit that initial particles file. And that's just X, Y, Z locations. I suggest keeping the Z at 0.5.
Yep, and how many particles you want. So, yeah. One other cool thing is that we can turn on hyper for the previous example.
OK, let's go ahead and do that.
So when we previously looked at this Mac projection example, which let me go back to the movie so that we're clear on that. So we've gone through a few things pretty fast. That's this example. So first we solve a linear equation to find what the velocity field is for incompressible flow around these embedded boundaries. And then we advect the particles through it. So for that first step, let's run this again.
Do you want to make that window wider so they can see? If you make it wider,
oh, the
make that window wider, they'll be able to see the
sure.
the output more easily.
So right. Yeah, let me go here and change the width. OK. All right. Is that better? All right. So let's run this again. Let's give it all 4 processors. Main 3D and inputs. Oh, actually, I think we need inputs 3D. So we see a bunch of stuff printed, and then we see time stepping for the particles. Let's actually save this to an output file so we can go and look at what this output is scrolling by. So first, it says how many objects we specified. This is all 9 by default. And then we're projecting the initial velocity to find the flow field around the obstacles. So this is done with multigrid right now. And you can see it's single level, and then it's going through the multigrid iterations to solve for the velocity field. And so this is with the geometric multigrid solver inside AMReX. And this solver is it can also be coupled to hyper as a bottom solver. So you can turn that on, running this with use hyper equals 1. Let's save this to some output too, because this will scroll by fast. All right, so this is much the same as before, but something different happened. So let's look at that. Now we're calling hyper, and we're using hyper to solve for the velocity field inside this multigrid solve. So this is a cool sort of package talking to another package feature that you can exploit. OK. I thought that was cool to show.
So
yeah,
there's actually something really unfair about that example. So if you guys have this and you grep for the word solve with a capital S, why don't you do that in your outstar.txt. So the solve time is the time that is spent in solving the multigrid equation.
grep.
And I'm actually a great believer in truth in advertising, which is why I want to make this point. Just grep.
Can somebody remind me how to use grep? I use ACK. So
grep. Get rid of dash E. Capital, no, just get rid of the dash. Capital
Right.
S,
all right.
OLVE,
Oh, OK.
space outstar.
Outstar. All right. Okay.
OK. So if we look at the word solve, how long did it take with the native solver? That very last one, 0.47 seconds. How long did it take with the hyper solver? 2.9. okay? So if you look at that, you say, oh, wow, Hyper's a piece of crap, right? Now, the Hyper folks aren't here to defend themselves, although I don't know if Ulrika's on the line. Ulrika, are you there? She's in the chat window. She's screaming right now. Because this is a totally unfair test. So one of the takeaways from this is we've demonstrated that AMReX can call Hyper, but there's always some sort of cost. There's always some sort of overhead. One of the ideas, this is when you come back to the 1 and 1 is 2. Hyper is a great solver. The AMReX native solvers is great. AMReX is a great, AMReX package. You put them together, the and matters, because one of the things that Hyper does is it spends time doing a setup so that it can do multiple solves. So Hyper is investing in the future right now. And that's all captured right here. In that 2.9 seconds, Hyper's investing in the future. It's creating a bunch of stuff that if you now call this on bigger problems multiple times, you might see a win. AMReX says, hey, this is an easy problem. I'm going to solve it. I'm going to throw everything away. I'm done. And so one of the takeaways here is kind of know what you're measuring. Because if you say, oh, well, why would I ever use Hyper, you would actually be wrong. And there are problems where the AMReX native multigrid, it's a geometric multigrid that doesn't have some of the adaptive capabilities. It will take much longer. So it's, again, an example of knowing what do you need. And if you're only running a small problem, you're doing it once. Maybe just use your native, whatever, or maybe even a handwritten. If you're doing something bigger, harder, more complicated, the package can still be a win. So I wanted to make sure that I pointed that out. But again, the idea is also, we think about having to link these packages. The honest truth is getting AMReX to talk to Hyper took some time. In the AMReX source code, there are pages of code of interface of AMReX calling Hyper. Again, Sundial's talking to AMReX. You're going to hear about, there's code that somebody had to write that says, OK, Sundial's has data structures, AMReX has data structures. How do we make those talk? The idea is, by the time it gets to the user, it's as simple as a command line. Don, do we have any other takeaways, or I think we're done?
I think that's about it.
OK,
Yeah.
we're going to finish early and give Dan some time to set up. Thank you.
All right.